I want to start with the part that you didn't expect. So I want to look at how can we analyze multiple flows over the same object in a way that we can actually get actionable insights. And then I want to look at the other two parts, right? Multiple objects, and then, well, this one here. So let's get started. Here's a very simple case. Who knows this data set, this model? 1, 2, 3, 4, 5. A few hands I see, right? So this is the road traffic fines management process, one of the public data sets. It's a rather simple process compared to many of the other real-life data sets. And here you see the three main flows. So if you drive too fast, you get a ticket. So it's a fine is created. And you can pay it on the spot or, well, with a bank transfer. Or if you don't pay, then after, well, on average, about 90 days, you get a letter, fine is sent to you. Then either you pay them or, well, fine notification is inserted and it's a penalty added, and maybe then you pay, but really, really much later, or things are sent for credit collection. So that's the process, right? I want to show you how to look at this differently. What we're going to do, right? When you animate, when you press this play button on a process mining tool like Disco or Slowness or Prom, you see these nice tokens flowing over the edges, and it gives you a feel for what's going on in the process. So let's follow one token, but not in an animation, but by drawing it out on a canvas. So I have the time axis on the x-axis. On the y-axis, I'm putting, here is create fine as an activity, and here's send fine. So if I have a case that was a create fine at time tc, well, sometime later, it reaches send fine. So I can draw this diagonal from this point to that point. Super simple. All I need for this is my classical event log. Case identifier, activity, time, nothing else. If I have a second case, and of course I do, then this may start earlier and finish later, for example. So if I do this for the road traffic fines data, I get this picture. Now comes the interactive part. What do you see here? What do you see in this picture? I'm going to switch to a whiteboard. We're going to highlight and annotate what you say. Yeah, so you're talking about this one here, right? Yeah. And then there's another one over here and over here. What do you call that? That's batching. That's batching, right? You let work pile up, and then you do it in one go. We know this is an efficient way of doing repetitive work, right? You want to stick in your mental context and kind of just work down things. Now, probably here, this is not a human doing it. This is an automated system, right? This is sending letters. So you're sending letters by the bulk because it's cheaper, right? So they're accumulating, then they're sent out. So there's different reasons for doing batching. And here you see it. You don't see this on the left. You can't. Well, maybe if you run the play button and watch all the tokens, then maybe you catch it. But yeah. This one shows it to you. Well, what else do you see? There's more. Is everything batched? It's the first example. No, there are cases that are not batched. They're going straight through. Apparently, not all traffic tickets are equal in my process. Well, I don't know why, but at least now I can talk about it, right? I have a means of communication that allows me to go deeper into the process and the organization to say, okay, well, what's going on here? Does this matter to you? Do you want that? What else do you see? There's a standard delay for adding a penalty. Exactly, right? So, and it's fixed, right? So you see strict FIFO queuing here, right? So it's there in 60 days. After 60 days, the penalty is added. Now you're wondering why this is orange, right? So we use these colors to indicate in which quarter, which of the quarters of the histogram the duration is. And this is daylight savings time, 1 hour more, so it shows up. Other things you see. One that is slightly more difficult to catch. I'll help you. So here we have this batching moment. And then these cases go out. And then we have the penalty that's being added. But here work accumulates. Because of this batching moment here at the top, I get still a larger amount of cases reaching then the add penalty step at that moment in time. And you see in the step to payment, then, well, there are people who do this very fast and people who do take much longer. If this wasn't the payment which the customer is doing, but somebody else within the organization, there would be an indication that the batching here is creating a workload peak down there for other people. You don't see this in the process models on the left. We can go on, right? One of the things that is nice to see, like here at the top, this is payment behavior by customers, right? So it's very irregular. And maybe it's also interesting to study which customers interesting, offenders, the people who have to pay, right? So who is paying fast, who's paying slow, whereas the rest of the process is really quite nice structure, right? So things are kind of in a rhythm. It's a good sign. So this is the first super basic technique for multidimensional process analysis. And if you look at different processes, you get vastly different performance spectra. Well, this is no surprise, but at the other hand, so seeing it kind of reveals a few things. So this BPI 2012 and 17, you see much more straight-through processing, quick things being done. The reason behind it is actually a bit more complicated, but these two processes come from the same organization, right? So you see these two processes are similar. Some of the things haven't changed in this process, also in terms of performance. Hospital billing, well, it looks a lot like this payment segment. We call this a segment, right? From A to B, we call this a segment. This payment segment, they all look the same, right? So lots of fast and slow overlapping. So maybe the characteristics of how getting a fine and doing the payment, these characteristics here are very similar to what's happening here. Though here, this is an organizational process, right? It's structured. So you wonder what's going on. Why is this so slow? Maybe there's too many customer steps involved or something like that. So you can analyze processes and compare processes in this way as well. It's very, very different from comparing control flow models. Then, of course, you maybe want to do machine learning on it, right? So here, I want to show you a few things where you can, well, I've shown you pictures, but let's do something with it as well as with algorithms. So one of the things we've noticed first were batches. So we can detect batches. The basic idea is that you're looking for a subset of the cases. It has to be a minimum number to be meaningful, that end in a very short time window. And, well, one of the definitions is they don't overtake each other, right? So FIFO, and then they end here in the small spot. Another option, recently developed by a student that I supervised, to kind of look at the relation between the opening and the closing interval. So then you don't have to look at so much thresholds. It's a bit more robust. And that allows you to kind of take apart the data and look at the cases that end up in the batch and the cases that are not batched. So you can categorize them now. And you can use this, for example, for prediction. I'll just sketch this very briefly. So one of the things that you can apply this on is analyzing how good is your predictor. So here in the black, you see this last segment of this credit collection process, where after penalty, things are sent for credit collection. In the black, you see what's actually happening. So there's two large batches, 2 batch points. And these blue and red lines is what the best remaining time predictor, back then when we did the study, was capable of doing. And you see this doesn't know batching. We never told it to know batching. So it wildly under and over predicts, and these are months, right? So this is not hours, this is months off in the prediction. So what you can do is, right, you identify these batches, then what's a bit more difficult than you locate in which part of the batch a case is, so you can estimate how much time it's going to be until it reaches the batching point. And if you add this into a longer feature extraction pipeline for a remaining time predictor, then what you get is that things improve. So the absolute error goes down from 230 to 177. It's not great, but well, it shows a bit. And the predictions are closer to the actual batching points. If we would have perfect knowledge of the batches, right here we're estimating the batches from historic data, but if we would have the perfect knowledge of the batches, this is how this would look like. So well, if you can analyze, you can check, are my models doing any good? So it can help.